Hey, everyone. Final talk of the day. Okay, great. So final talk of the day today will be from Conrad, and then we'll move on to the hack session. So take it away.
Cool. Yeah, hi, I'm Conrad. Some of you may know me. Should I take this one?
Yeah.
It's all right. So, cool. Is that good? Yeah, some of you may know me as a Phantom developer, maybe like 4 or 5 years ago. That was something I was working on sort of alongside my PhD because it was something I was interested in. I'm also joined here by Dave today, who did his PhD working with Phantom. He put GR into Phantom, but today we're here sort of representing ADACS, Astronomy Data and Computing Services. And so we'll sort of talk about the work that we've been sort of, as a collaboration between ADACS and Phantom. The purpose of this talk really is to sort of bring you up to speed on what our involvement has been. And so I'll talk a little bit about some of the testing that we've improved in Phantom via CI/CD, which most of you may be familiar with, and also our implementation of MPI and OpenMP, which has really been sort of come out of the need for higher performance and larger simulations in Phantom. Since it's going to be Valentine's Day tomorrow, I'm going to talk about why I think Phantom and ADACS are a great match for each other. But perhaps before I even get to that, maybe I should explain sort of who we are, who ADACS is, at least in the context of Phantom. So we provide software development services for astronomers, astrophysicists, people just like yourself. So our work is done through a merit allocation program. So essentially comes at no cost to researchers. You just apply for our time, and a merit allocation committee grants you that time, and we collaborate with you to sort of solve your code problems. We might be building databases or web pages, or optimizing your code. And our services are available to anyone in the research community. You don't have to be a professor. We work with a lot of PhD students who are having code difficulties, and we sort of collaborate with them on that. And so our team is comprised sort of two main groups, former astrophysicists like myself and Dave. So we did our PhDs in astro. We understand, or we try to understand the science, and we sort of understand how scientific workflows go. And the other half of our team is professional software developers. So they come from more of a computer science background, and having them on our team has been so beneficial because they're always promoting the best software development practices. They're always teaching us about the new tools. And so whenever we work with researchers, we get to carry those practices through and introduce them into your codes. So why are Phantom and ADACS a great match for each other? Working with ADACS means that you can worry about your science problems, and we can worry about your code problems. So as a PhD student, the last thing you want to be doing is spending 2 years trying to debug an issue in your code, or you find out the code's not running fast enough, so you're rewriting the whole algorithm, and you're not actually doing your thesis at all. You're not answering any science problems. Sort of, we exist to mitigate that a little bit. At the end of the day, you will be rewriting the code, and that stuff is really important. But let us worry about your bugs, the performance optimizations, and you can focus on your science. We're also, at least like some of the developers on our team are also sysadmins at OzStar Supercomputing. So myself and Dave, we work day to day in the data center. We understand the full stack of supercomputing hardware. So we unbox the machines, we rack them up, we build the operating systems, we install the software, and then we help you develop your software to best target that platform and optimize for that. And so I believe that that's a really unique position. I would encourage you to take advantage of that, because when you're writing codes, you're not writing them necessarily to run on your laptop, you're writing them for a supercomputer. And when you're doing that, you sort of want to talk to people who know that hardware well, so you can take advantage of it. And we just really love working on Phantom because the developers, the users, all of you really understand the importance of testing in the scientific workflow. And that's evident in the fantastic test suite in Phantom. And that's actually a breath of fresh air. It's very, very rare amongst the scientific sort of computing community. And also just SPH, it's an interesting algorithm. You're solving cool science problems. And at the end of the day, like we find that interesting. So it's a real joy to work on. Here are some of the contributions that ADACS has made to Phantom so far. It's a bunch of pull requests. You may have seen my name or Dave's name on GitHub a little bit. I won't talk about all of these things, but I will go through 2 of them today. And the first one is going to be testing. Yeah, whenever we sort of start a new project at ADACS and we're meeting with the science team for the first time, the very first question we ask, or one of the first questions we ask, is what sort of test suite have you set up with your code? How are you testing your code? How are you making sure your answers are correct? And we stress this a lot because you can't do any code development without knowing that the answers are correct after your changes. So this is the Deep Space 2 probe that NASA sent to Mars in 1999. And this mission was ultimately a failure because it crashed into the surface of Mars and they never could regain communication with it again. And in the post-mortem of this failed mission, NASA sort of they dissected everything and made a bunch of lessons out of it. And one of these is test as you fly, fly as you test. The process of end-to-end system verification may be compromised when it is not consistent with the mission profile. In the context of sending rockets up into space, test as you fly means that you should build tests for your system that mimic the way you are going to fly your rocket. So if you're going to send it to a different planet, you should try to mimic the conditions of that planet. And fly as you test means that during a mission, you shouldn't attempt anything, or you shouldn't try to fly your craft in a way that wasn't validated during your tests. And so the team failed to do this and the mission failed. And I think for many of our software development projects, we can take the same principle and apply it to the same way we write our code. Test as you fly in the context of writing code might mean we want to write tests that simulate the conditions that we want to do our numerical simulations in. So we want to write unit tests to make sure all the physics are correct. We want to do simple tests where we know the answers, and these tests should be relevant to the simulations that we're running. And fly as you test means that when we're using the code, we shouldn't push it beyond the regime that it's been tested in. So if the simulation you're running hasn't been tested for certain densities or certain number of particles or things like that, you should be really, really careful with that, because it's entirely untested. Fortunately, we're not flying rockets, so failure doesn't mean we crash into the surface of Mars. Failure just means that we publish junk results, which is probably not as critical. And you'd be surprised how many codes we work with don't have any tests at all. Fortunately, Phantom, when I first started working on it, had a reasonably good test suite. Daniel had set up a nightly test script that essentially ran every single, ran at midnight. It would check out the master branch on Git, run a pretty comprehensive set of physics tests and just unit tests to make sure everything was good. And then in the morning, if something was wrong, you would get an angry email from this robot telling you what was wrong. And that was pretty good. It caught a lot of mistakes, but there's a few issues with that. And that's actually been improved upon since then. Current Phantom runs continuous and rapid testing for every single pull request you submit. And sort of implicit in that is Phantom has now moved to a pull request workflow. And that means that you no longer have bad code pushed into the master branch. Previously, tests would run on the master branch, which means that you could be waiting 24 hours before you were notified whether a commit was bad. And during that time, anybody could have been checking out the code, using that code, not realizing that there was a bug in it. And there could be running real simulations using broken code. With the new pull request workflow, developers now get notified usually within 90 minutes, often much sooner if your mistake is quite simple, whether your pull request fully passes the tests. And during this time, the master branch remains fully stable. So while you're trying to develop a new feature, that's not affecting anybody else's development or anybody else's simulation. And if you use the pull request workflows, all of this is really, really obvious. This is nothing special to Phantom. Pretty much every software development project around the world uses this. But again, it's very rare in scientific sort of software development. So that's sort of one of the reasons we like working with Phantom. And one of the reasons we could get that time down to 90 minutes was we're now running those tests on the GitHub infrastructure. So we no longer run those tests on local hardware. That's all done in parallel on runners in the cloud. And basically all of this rigorous testing, we sort of insisted on it when we started working with Phantom because it provides you the foundation to overhaul the core algorithms in Phantom. When I say core algorithms, we're not just adding a few post-processing features here and there. I'm talking about we're tearing the density routines apart, we're tearing the force routines apart, we're rewriting them from ground up. And you can't make drastic changes like that without knowing that every step you make, you're not breaking the code. Because again, if you're going to make some optimizations to the code, but you're going to change the physics, there's no point doing it at all. So that really set the foundations for sort of the next optimizations that we were going to do, and that is applying parallelism to Phantom. Sort of speaking to many users, at least I hear it directly through Daniel, that people are beginning to run simulations with more particles. They're wanting to run simulations for longer simulation time, which means it takes longer wall time. And people just don't want to spend months waiting for the simulations to end. Or they just can't run a particular model because it's got too many particles in it. And so that's sort of where MPI comes in, because it enables the code to scale beyond more than one node on a supercomputer, which will make it faster or just make large simulations possible. Phantom is already a parallel code. It was a parallel code before we started working on it, before ADACS started working on it. And that parallelism is implemented using OpenMP. It's done in a very fast and efficient way. By efficient, I mean uses very little memory and there's very small communication overheads. So when we wanted to take MPI to scale this code up beyond more than one node, we want to preserve the existing efficiencies in Phantom. We didn't want to sort of lose them just to achieve a greater scale. And so, for example, what this might look like is each node on the supercomputer, so each machine runs one MPI task, with each task running several OpenMP threads. So if your machine has 32 threads, for example, there'd be 32 OpenMP threads on there, and each machine runs one task. The challenge here is, how do we get each thread to send MPI messages under the same task? I sort of don't really want to dive into the MPI sort of standards documentation, and maybe many of you don't even really care about how MPI is implemented. You just want to use the code. So I'll try to explain this with a nice, simple analogy. So consider this cookie cutter neighborhood where every house looks the same. You can consider each house like it's a node on the supercomputer. And each person living in the house, you can think of like a core on the supercomputer. And communication inside the house is really easy. So take, for example, you have a housemate that you live with. You share all your resources. So you share a fridge, you share a TV, you share a couch. That's sort of like sharing memory in OpenMP. It's really fast and it's really efficient. And you can talk to your housemate really easily. You just yell across the room and they get the message. But if you want to talk to your neighbor who's in a different house, then that's a bit more complicated. You have to pick up the phone, you have to dial the number, You have to wait for the phone to ring, and maybe if they're not busy, they'll pick up the phone, and then you can talk to them. That's sort of the way MPI works. There's a lot more communication overheads, but it lets you talk to a much larger group of neighbors. And that's sort of how Phantom's hybrid MPI and OpenMP implementation is done at the moment. You have density and force interactions when they're really close, they're on the same node, and they're done with OpenMP very quickly. When they're further apart, they're done with MPI. One of the challenges we're facing at the moment is, so on the left-hand side here, each thread waits its turn until the communication buffer is free to be used. And so this is done using sort of OpenMP critical sections in the code. If we go back to the house analogy, that's like your housemates using the landline phone. So you can't use the phone to talk to a different neighbor at the same time. You have to wait for them to finish, put the phone down before you can dial someone else. And that presents a real bottleneck. Thanks. Especially if, say, you've got many more people living in the house. Let's say you've got 30 people living in the house. You start getting a big queue for this phone. And maybe if we explain it this way, the solution is pretty obvious. Just give everyone a mobile phone. If everyone has their own phone, they can all perform the communication independently. And you can dial people whenever you want. So that's the proposed solution that we're moving towards in Phantom. That's with parallel communication. And the only sort of MPI bit of standards documentation I'll talk about here is this feature called MPI thread multiple. That's a switch that makes it possible, and we're investigating that at the moment. We think it might have sort of performance overheads, and it's not necessarily supported everywhere. So we have to make sure that it's widely used enough in various MPI libraries and supercomputing facilities. But we think this is going to be the solution. This is still a work in progress. And so if you're interested, you can have a look in pull request number 310 on GitHub. But that's where we're at on our roadmap to better parallelism in Phantom. Phantom started out as a pure OpenMP code. And then we implemented sort of an MPI proof of concept to show that, yeah, we can achieve better scaling. And that's where we are now. We've got MPI and OpenMP working in tandem, but with this serial bottleneck. And the next feature that we're adding to Phantom is MPI and OpenMP with sort of parallel communication. Just in summary, if you think that your work with Phantom would benefit with parallelism, so you want to run more particles, you want to run larger simulations, or you've got ideas about how you think Phantom can improve its performance, or you've just got like a different code problem and you think you would benefit from ADACS software support program. So Dave and I would really love to chat with you during some of these hack sessions. We'll be here the rest of this afternoon and during the week as well. Thank you.
Thanks, Conrad. Does anyone have any immediate questions about ADACS or parallelization?
I'll make just a comment. So, I mean, a lot of stuff is under the hood for everybody using, but say, for example, that the fact that everything gets checked really quickly on a pull request now is amazingly good, and it checks a lot of things. And that's really like these guys implemented that without any of us having to do the work. And it's just a wonderful thing. You get the green tick, it goes in. And as you say, it means actually, I know people take like code versions from ages ago, but it doesn't mean the master branch is very stable. So it means that if you just git clone the master branch, it means it's really safe code to use, and we'll run everything that's in the test suite. The other thing I was going to ask as a question, I mean, you didn't mention you guys have done a lot of profiling. I wonder if you still have it, whether you might be able to show some of those results, maybe not immediately, but.
I don't have the graphs on hand.
Yeah, I think Dave's definitely got them. I mean, I've got them lying around as well, but maybe, I mean, Dave, if you can show us maybe during, if you're still hanging around this afternoon, I think it would be helpful for people to see the practical, what the practical performance is, because there are some problems where MPI actually does, it makes it go faster and works well. It's not true for all problems, and self-gravity is probably the limiting one at the moment. But if you've got a problem that's not self-gravitating, there's some strategies as well that you guys came up with like you don't necessarily want to use one MPI node for 32 threads. In your analogy, you want to make, maybe you want to explain, you make smaller houses or something?
It probably falls apart if you, if as in the analogy falls apart.
You don't want more than 8 housemates.
Yeah, too many housemates is bad. But yeah, self-gravity is a really tough problem because the gravitational force travels infinitely, and that means every particle starts needing to interact with every other particle instead of its just nearest 57 neighbors. So it gets a lot more expensive. But yeah.
Okay, so just following up on that, there are a lot of cosmological codes that do n-body stuff that scale well, you know, with self-gravity. What is it about Phantom that makes it so difficult?
So a lot of cosmological codes, we're talking about the ones that scale to like thousands and thousands of CPU cores. Most of them are pure MPI codes. And most of them have relatively, so Daniel, correct me if I'm wrong, but most of them have relatively simple physics. And Phantom at the moment is very, very efficient with OpenMP. And so if we were to switch to MPI, a pure MPI implementation, within a single node, so let's say you only have 32 cores, going to 32 cores with pure MPI, you would take a severe performance hit. And so we wouldn't want to affect that, but we still want to be able to get that scaling. So that's kind of where the tension lies.
Definitely one of the limiting things is how much information per particle you're trying to communicate. So, for example, if you're doing hydro, dust nucleation, all this other stuff, you've got many things per particle need to be sent when you pass a particle over to somewhere else. But if you're doing dark matter, you just got to send, I don't know, a mass and a position. So it's a bit cheaper in that sense. And even for, say, self-gravity, so one thing they do, which is they don't even compute like the moments of the gravity from a node. So they just send the center of mass and that's it. And don't bother with the quadrupole moments and things like that. So
maybe you could tell people who are interested in using ADACS how they can apply for time.
There is sort of information on the website at adacs.org.au, but I would really just encourage you to come and talk to me or Dave, because we can sort of, help you connect to the right people to do that, and just determine whether or not your project is a good fit. It probably is a good fit, but we would help you figure out like which way we would best be able to help you with.
Thanks. Anyone else have any questions?
just one more comment, maybe on those pull requests, you had your list, Conrad.
Most of them are bug fixes.
So you see the thing down the bottom, the second line, second last line is just a whole lot of bug fixes. Now these things take quite a long time to like find and dig out, and I just, I mean, it's not, what's the word? It's not glorious work, but it's really valued. So like, thanks for that.
Okay, so thanks, Conrad, and thanks to all of this afternoon's speakers.